a lot of
Cordian,
yes.
sorry, excuse me. Did you share the screen?
I shared the screen. Don't you see the screen?
No, it disappeared. Share again, share again. Sorry, it was
Okay, yeah,
disabled.
that always see this is this is the problem because we're all do you see it now? Maybe I redo it
Yeah,
again. Sorry.
yeah, it disappeared. It appeared, but now disappeared.
Yeah, that's we are mathematicians. We are very smart in many cases when it comes to theoretical questions, but then whenever, and I know there is a theoretical solution to this problem, but whenever it comes to the practice of sharing screen via, do you see something now?
Something really red. Now we see. Now we see.
Perfect.
Yeah, yeah.
Very good.
Symmetry is
So I'm
enabled.
using again this iPad on the side with hopefully gives me the possibility also using the pen. So what I wanted to say is that it's maybe a good point to be a little bit more concrete today after that I've been very theoretical the first two lectures, and we will be more concrete also tomorrow in the theoretical lectures again. But let's maybe work together on a concrete problem. So the first question that I have, I see half of the people in the room maybe. So if I now ask you to raise your hand, I only see half of the people. But who of you has a computer with him or with her? Okay, I see at least one hand. Okay. Do you have a computer algebra system on that computer? I mean, you don't need much. You just need to compute matrices. Can you compute matrices on that computer? Do you have Sage or Maple or anything on the computer?
We have gap.
Okay, very good, very good. Because then you will be now my guinea pig, or I'm sorry for that. Don't worry, it will not be very harmful. So hopefully. Um, because so yesterday or the day before yesterday actually already I started with this very beautiful example of this circulant matrix, and I talked a lot about it as a motivation, but I felt that we actually never have explored this concretely. So today I would like to use this tutorial to actually do a hands-on experience with how actually we get to this example. So remember, I told you that when you look at this matrix where these coefficients are indeterminants, so we don't, these are not numbers. I mean, they will be variables. Um, you can actually still find a factorization of the determinant that is very beautiful, which is the one that you see here. So I mentioned this, and implicitly, I mean, if you have really followed the lecture and you have worked at home and you really wanted to understand this, I'm sure you have succeeded doing this. So then this next 45 minutes will be maybe just a repetition for you, but this is very good because repeating stuff never hurts. But for the others who have maybe not had the time to look at this more carefully, I hope this will be actually one of these moments where things click in your head and you will say, oh, this is actually much nicer than I had maybe thought after the first lecture. So the question that I want to answer is this question: why is this actually true? And today, in continuation from what I had on Tuesday, I actually now want you to know why this happens. Okay, so coming to the person in the audience, or to the two persons at least in the audience who have a computer, I would really like to do a concrete example. So the concrete example that we will look at now is when we have a 4 times 4 matrix. So can you maybe set up in your computer this 4 times 4 matrix with the 4 indeterminate C0, C1, C2, and C3, or you can call them A, B, C, D, whatever you want. And for all the others, I mean, this hopefully takes only some minutes. I briefly go on. So we will now look at this example. This is a concrete example, of course, but I promise you that once you have understood this example, it will be completely obvious what to do. Okay. So let's look at this. Let's look at this matrix, and let's look at another set of matrices. Namely, we have talked a lot about representations, and we had also talked about the cyclic group. So I want now also to look at the cyclic group of order 4. So this, remember, is a cyclic group. That means it's generated by one element and its powers. So we have these 4 elements, g to the 0, g to the 1, g to the 2, g to the 3. And to make a concrete matrix representation, we need to find, I want to have a 4-dimensional representation of this group, and I want to do this concretely with matrices. So we have to find a 4 times 4 matrix that we associate to my element G, and then we can uniquely associate to the other elements the powers of this matrix. So the people with a computer maybe also want to write down this matrix as our matrix G. Okay, so we have this matrix C4 that we're actually interested in, and now I played in this other family of matrices. So these are implicitly defined 4 matrices, all the 4 powers of this matrix from 0 to 3. And we have already seen that this is a representation, and by definition, this is the representation of the cyclic group of order 4. Okay, why did I do that? Okay, so let's look at the following. So I claim, and I would like you to verify this for me, at least in one example. I claim that the matrix that we started with, this matrix that we have here, this matrix, if you look at this matrix has a very nice property. If you look again, the lines in this matrix, they're all cyclically shifted. I mean, this is how I motivated this matrix yesterday. And what this translates to, with the help of this matrix representation of the group C4, is that actually we have that when I take my matrix C and I multiply from the right with a matrix mg to the power I, it will be the same as if I multiply from the left. Okay, so I take a matrix, and this matrix does not change. I mean, this matrix changes when I of course when I let the group act on it, but the change of the matrix, it commutes with these matrices, right? I mean, this is a form of commutant. So it doesn't matter if I multiply from the left and from the right with this matrix for all the matrices in my representation. So another way of saying this, I mean, a little bit more algebraic way of saying this, is that this matrix C4 lives in the commutant algebra of this representation. Okay. Have you verified this at least for one of the examples? Now I would like to see a head noting. Somebody
Yeah,
noting
can you
that.
go back to previous slide, because I was just noting down.
Oh, don't worry. Yeah. This is now a very relaxed time. So you can always interrupt. So I only have 17 slides, so this is not a lot of slides. Don't worry. But it's meant for you to, I want you to, I mean, I don't want to get through all the material maybe, but I want you to get this moment where you say, oh, I finally realized this actually makes sense. The matrix that I defined here, you see, this is just the cyclic permutation that I have defined here. So it just maps 1 to 2, 2 to 3, and so on. Okay, so how many people actually have a computer now? I don't see how many people have a computer and do something. Very good, very good. And I hope the other people don't get bored so much while the other people take a little bit of time writing down these matrices. You can also do this by hand, of course. 4 times 4 matrix multiplication is doable by hand, but I advise you to use a computer because it's just a little bit faster. I also see that there is people in another room that I can see. Sorry, I have not seen you so far. I mean, I have seen you, but not focused on you. Does somebody in your room have a computer? These are the people in IBA main campus. I cannot hear you, so if you have a computer and you do something, please raise your hand. Okay, maybe something happened. No. Okay. Okay. Are you done with is everybody done? Carlos, are you not doing something?
I'm here.
Okay, very good. So let's go on. Let's go on to the next slide. Very good. I'm sorry, okay. So as I said, as I promised you, and I hope somebody has verified this matrix that we have defined C4 has the property that it commutes with all of these matrices that I have defined for my matrix representation. Okay, so what is the mission of this tutorial? So I'm a missionary and I want to bring the gospel of representation theory to your heart. So the mission of this tutorial is actually to set in stone one thing for the rest of your life. Whenever in your life you will come up in the situation that you're interested in a matrix, like this matrix C4 that you're interested in, that has the property that it commutes with some other matrices that come from a group representation. So, I mean, if you're able to formulate a problem in this language, then I want you to remember, I mean, the best case scenario, all the lectures that you had with me, of course, but the least thing I want you to remember is one keyword. And this is, I want you to remember that there was this thing called Schur's lemma. Okay? Schur's lemma is the thing that I want you to remember, and this is the thing that is actually will help us a lot. Okay, let me briefly recall Schur's lemma because we went over this very, very quickly, and I was a little bit, maybe a little bit vague. As you remember, maybe the proof was very easy, and it was a very powerful theorem, but let's just remember what it said again. So we had two irreducible representations, V and W. I mean, V and W could be also the same irreducible representation. And we have a group homomorphism. So a linear map that interacts well with the group action, namely it commutes with the group action. It doesn't matter if you first take the group action and then the linear map, or if you first take the linear map and then the group action. Then we know that if these modules are irreducible, there is not much choice for this map, namely either it is the zero map or it is an isomorphism. So either those two are isomorphic or the map that I had is actually just the zero map. And the proof was very simple, so we don't go through the proof again. But so the corollary that we had was that we can make this very concrete for endomorphism. So let's take an irreducible representation of a group, G, and now a map from V to V itself that is an endomorphism, so that it still commutes with the group. Then we claimed that this actually is just multiplication with the scalar, namely it's just lambda times the identity for some lambda in C. So this was one of the corollaries that I invited you to prove, and I just give you the proof now because it's a very easy proof. So we know by the first part of Schur's lemma that phi actually has to be an isomorphism, right? I mean, it is an endomorphism, so it's an invertible map. For this to be interesting, I mean, it has to be an isomorphism. And let's look at an eigenvalue lambda of this phi. And we now look at another endomorphism, which is just phi minus lambda times the identity. Okay. Again, I take a matrix and I subtract lambda times the identity if you want to think in matrices. So I get a new homomorphism from V to V with zero determinant. Okay, which is with zero determinant. So this will not be an isomorphism, and one verifies very easily that it still will have the property that it commutes with this group action. So it's still it is still a group homomorphism. So we can again use the first parts of Schur's lemma to say, well, then this identity actually it's not invertible, it's not an isomorphism, so it has to be the zero map. So because this has to be the zero map, it just means that my phi actually has to be lambda times the identity for some lambda in the complex numbers. Okay, so in other words said, this just means that if you look at the matrix of this isomorphism phi here in an eigenbasis, you will find a diagonal matrix in a way where you have all of the eigenvalues are the same. There are some lambda in C. And let me just recall that we have one prerequisite here. We have to have that the field we're working on is algebraically closed to making sure that we have these eigenvalues. But we always assume that we work over the complex numbers, and I just mentioned this because maybe at some point you're interested in a situation where you're not working over the complex numbers. Okay, why did this help us now? So I also mentioned day before yesterday that we can make this whole theorem a little bit more concrete with matrices, and when we have more than just one irreducible representation. So now let's assume I have a general representation. I have a general representation rho that is given by matrices. So, and I have a matrix X with a property that it commutes with all the matrices that I get in the representation. So this is exactly the property that I had for my matrix C4, or more generally for the matrix Cn, when I take this row to be the representation that we chose of the group C4, or more generally for the cyclic group Cn. Okay? So this is exactly the situation that we're actually interested in. And we assume further that we have, that by some knowledge we know that this representation decomposes in the following way, namely it is M1 times some irreducible representation rho 1 plus and so on times MK some irreducible representation rho k. So at some point we called this also the isotypic decomposition of my representation, and I mentioned that this is unique. And let's further assume that we know the dimensions of these irreducible representations. So I mean, just a nice person that we met on the street gave us this information, let's say. Okay, so what we can then deduce from Schur's lemma, and in particular, just by generalizing the arguments that we use to prove the second part of Schur's lemma here, is that we can actually find a so-called symmetric adapted basis, a symmetry adapted basis for my vector space, which is Cn in this case, which block diagonalizes the matrix X. Okay, so block diagonal, we'll see in a moment again what this means. So this just means there exists a matrix T, which is the base change matrix, such that I can define a new matrix Y, which is T inverse xt. So this is just the base change here that we do that has a block diagonal structure. Namely, it has k blocks of this dimension corresponding to the irreducible representations, and further these blocks decompose in equal blocks by. So this is a lot of information. Let's make it a little bit more concrete. I mean, a little bit more pictorial. So it just means that after I find this basis, some nice person on the streets may hand me that basis T, and after I do this base change here, if I do this base change here, which I can again use linear algebra on my computer for, I get a new matrix Y, and this new matrix Y will have a very particular form. It will be a matrix that has a lot of zeros, namely it will be the block diagonal, and by block diagonal I mean that I have some matrices y1 to yk. So these are in general not necessarily just numbers. These are themselves matrices, and these matrices again come in a block diagonal structure, namely they have the same matrix bi on the diagonal. And here again, bi is can be a number, it can be also an mi times mi matrix in general. So I have k irreducible representations. These k irreducible representations give me k blocks. Each of the blocks further decompose in blocks, and the dimension of these blocks is exactly the multiplicities that I have here, these mi's, and they span the dimension, and I have dimension many of these same blocks in this subblock. Okay, so showing this requires just a little bit knowledge of linear algebra and just a repetition of the same argument that we did previously for the second part of Schur's lemma. So the important message is not to remember all of the details, but just to remember, I mean, there is this decomposition, and somehow out of this decomposition, we could have found a basis. And once I use this basis, my matrix that I get after the base change will be much simpler. Okay, and how much simpler will it be? Well, I can get all of the numbers knowing the explicit decomposition. Okay, so the question that, of course, the people with the computer and hopefully everybody else might ask themselves now is, but okay, now again, he's talking about so much theory. How is this related to our matrix Cn? Well, let's look at this matrix Cn again. So this matrix Cn commutes with all these representations mg. Okay, and G was the cyclic group, and a cyclic group is an abelian group. So the first thing that we have to see a little bit is what are the irreducible representations of abelian groups? And the first thing that we can notice is that actually those are very simple. So yesterday I mentioned, or the day before yesterday, I'm a little bit behind time always, sorry for that. I mentioned that in general, I mean, there is no reason to assume that irreducible representations are always of dimension 1, but I gave you as an exercise to show that for abelian groups, you will always have that the irreducible representations have to be of dimension 1. And this is a very simple proof again. Let me just quickly show you. I mean, if I have an abelian group, what does it mean to be abelian? Well, it just means that all the matrices, all the elements commute with each other. So G times H is the same as H times G, which translates via the representation that also the corresponding matrices commute all with each other, right? I mean, they all commute with each other. So in particular, a selected matrix rho of G will be having the property that we had for Schur's lemma. So it will be of the form C times diagonal C times an identity matrix. So if I for some complex number C, so if I apply this matrix to any vector, I get that this vector will be C times V for any G. So actually, what one sees from here is that every subspace of V also will be G invariant. So also will be closed. I should have written will be closed by G. So will be also a G module of its own right. But we already assumed that V is irreducible. So because it is irreducible, we want to avoid that it can have any non-trivial subspace that is closed. So therefore, the only subspace that it can have is which is trivial, is in the trivial subspace and itself. So, and this then means that V is one-dimensional. So that was again maybe a little bit quick, but important message. If I have an abelian group, doesn't necessarily need to be a cyclic group. For every abelian group, you immediately know that the irreducible representations will be all of dimension 1. Okay, now let's look at the cyclic group. So the cyclic group, remember, is the group. It's a group that is given by one element, which has the property that if I take it to the power n, I get back the identity in the group. So this has exactly n distinct irreducible representations. Each of one is one-dimensional. Each of them is one-dimensional. We saw in the previous theorem, so they have to be one-dimensional because it's an abelian group. But how do we actually realize these representations? Also, this is not really hard to see, but will be important for understanding how our matrix actually can be diagonalized. So we know that it's one-dimensional. So all we need to know is, and our group is generated by one element, so I can uniquely specify a representation, rho k, just by knowing where rho k maps my element G to, right? So only by once I specify this number here, which is a number, I have uniquely specified the representation because I get everything else just by powering. But on the other hand, because of this property, we have that rho k evaluated at Gn has to the power n has to be 1. So in particular, we see that this has to be an nth root of unity. So the nth root of unities, they are just those numbers, that you know, the nth root of unity, and they're all distinct. And basically defining a representation in this way that I assign G to the m to the m's power of a kth root of unity gives me all possible irreducible representations. So this was also a little bit maybe quick, so it's very good to go through this again on your own, but just saying, I have these very nice irreducible representations for the cyclic group just by knowing all of these roots of unity. And the reason is just that a cyclic group is cyclic, so it better be mapped to a root of unity. Okay, very good. So let's just come back to our previous example. So I claim now that we could make a very, very bold guess. And we will see a little bit later how I made this guess. But now I invite again the people with a computer to please type in this matrix T in your computer. You can call it T, you can call it whatever you want, but please write in this T. And for the other people, please try to see why I came up with this matrix. Try to maybe relate this matrix to the previous theorem that we had. Okay, so the first row is a 1. The first row is a 1. The second row is 1 I minus 1 minus I, 1 minus I, 1, 1 minus 1, 1 minus 1, and 1 minus I minus I, minus 1 I. Sorry, now I'm really bad at reading myself because I and 1 is really hard to distinguish sometimes. So a quick question into the audience. Why do you think the numbers 1, minus 1 I, and minus I appear here? So if nobody answers this question, I'm afraid, I'm a little bit worried.
Roots of unity.
Exactly. Those
Fourth
are
root of
exactly
unity.
the fourth roots of unity. Very good. So, and now I made, as I said, this is maybe still a wild guess how I came up with this matrix, but at least the numbers that you see in this matrix may be making sense. Okay, so has everybody copied this matrix in the computer? I just hope that this is the case, because what I want you to do now is, we have this first matrix C4 that you defined. You have this matrix T. I would like you to now evaluate T to the minus 1 C4 times T. So do the base change with respect to this matrix T. And the first one to do this may shout out loudly in joy and report what she or he has seen. Or the people who do it by hand can also shout out if they're quicker than the people who do it by computer. If nothing happens, I'm a little bit worried here, but do you see anything? Again, I only see 2 people with a computer or 3 people with a computer, so I hope
So what do you want, Cordian? Was it T inverse times C?
T inverse times Cn C4 times T. And depending on, I mean, so hopefully I didn't mess this up now. This is now the worst example if it doesn't work, but I think I calculated it yesterday and it worked. So I hope it worked. So what happens if you do that? Any guesses?
It's C back.
Sorry?
C back.
You get C back.
C back.
I get C back. Why do I get C back? I mean, that would be very strange, no? I mean, I have this matrix here. I mean, this matrix is
What talk?
hopefully an invertible matrix. I mean, this I take its inverse and I multiply it
iota.
with C, and I multiply it again with this matrix.
Seemingly an
Sorry,
orthogonal
it-
matrix, so
You
the
get
inverse is
Sorry?
just a transpose of it.
no.
Sorry?
You get. Sorry, I was wrong. Sorry. You get a diagonal matrix with
Exactly. Very good. I get the diagonal
roots of
matrix.
unity on the diagonal.
Very good. So this was now, I mean, so this is the difference between, you know, normally me doing and just showing the slide and you actually doing it. Things take a little bit longer, but exactly what should have happened. And I calculated this yesterday, so I'm pretty sure that this should have happened unless I made a huge mistake somewhere. When we do these calculations, T inverse times C4 times T, I get a matrix that is diagonal. And if I look at the entries in the diagonal, I mean, I get the sum, I get this, I mean, I get this exactly, these entities that I had. I mean, these roots of unities in front of these different coefficients Ci, exactly in the way that I arranged it above here. And of course, now if I take the determinant of this matrix, I mean, everybody in the room, even the people without a computer, should now be able to compute this determinant. Well, because this determinant now just is the product over the diagonal, which is exactly this here, which is exactly what we were supposed to find. Okay. So I hope that this helped a little bit to make this click moment in your head to see, okay, it actually works. And now we actually see what we were supposed to see. But of course, here, how I came up with this matrix here was still a little bit mysterious. So I had some hints with these roots of unity and so on. So, I mean, maybe I just cleverly, and I already knew the result that I wanted to get because I knew the theorem. So maybe the matrix that I came up with was also inspired by what I wanted to find in the end. So we will now want to try to understand a little bit how we actually in general come up with this matrix. For this example, for general N, of course, but more importantly also, how do we come up with this matrix for a general group? Okay, let's again have a flashback to the first lecture. So in the first lecture, I told you that every G module can be decomposed in what we called an isotypic decomposition. So the isotypic decomposition was a direct sum of my vector space into subvector spaces that I call V alpha. So V alpha is one of these summons here. One of these elements here. So this just means I have n alpha times the same representation V alpha, W alpha. So V alpha is called the isotypic component corresponding to the representation alpha. And I also, I mean, you see this decomposition. And if you make up the proof of this previous theorem of Schur's lemma made very concretely, actually, if you go back, this decomposition, a basis for this decomposition, if you have this decomposition, or actually maybe it's better to point as if you have this decomposition correctly, so if you have a basis of V which is corresponding to a basis of V0, a basis of V1, and so on, till a basis of Vk, such that I get a sum that a basis that respects this direct sum structure here, then actually this basis will give us exactly those blocks yi. So here I have to be a little bit careful what I mean by this. This will give us these blocks yi. I mean, not yet in the final form that they are with these subblocks, but it will give us a lot of zeros already outside of these blocks yi. So it doesn't give the specific form of these yi's yet, but it gives the structure where we have these different yi's. And the reason, just for the people who want to understand a little bit more, the reason is that these subspaces that are here in different isotypic components, they are by definition all pairwisely non-isomorphic. So every morphism that goes from one of them to another has to be the zero map. So if you build up a matrix with respect to this basis, entries of the matrix that correspond to parts of a morphism going from here to here have to be zero. Okay, very good. So I also briefly mentioned the definition of a character. So a character, again, was the thing that we defined by saying I take a group element, I map it to a representation, to a matrix, for example, or to an element in the general linear group, and I take its trace. So this is a function that takes in as arguments elements of the group and spits out elements in my favorite field, for example, C. And we have already seen that I mentioned this briefly also already, although here I'm making some choices maybe to compute the trace. Whenever I have an isomorphism going around, then actually this will not affect the trace. So the trace has this very nice property that you can cyclically shift around these matrices here so that these two matrices actually cancel out, so that the trace of whatever I have here, conjugation, for example, here I have conjugation on the group, this is conjugation on the group, will give the same as if I don't conjugate with the group. Okay, so it is actually a so-called class function. So it's a function that only takes different values on different conjugation classes of my group. Okay, this is just for people who are interested. So this is what we call a class function. So why should you be interested in these characters? So these characters actually have a lot of important information that is important to characterize. I mean, that's why it's called character, to characterize a representation. So the most important one is, which is also a consequence of Schur's lemma actually, is the so-called orthogonality relations of characters. So if I have two characters that correspond to non-equivalent or non-isomorphic irreducible representations, I can look at their inner product. We defined this inner product briefly also in the first lecture. So this is just defined like this, and you may be having some reminders to yesterday's lecture. This also looks a little bit like this Reynolds operator that we had. So I define an inner product for these characters, which is just I sum. So these characters, you can think of a character as a vector. You know, this is a vector for every entry of the group, or actually for every representative of a conjugation class. I have an entry here, chi rho of G, and I just multiply these two together as I would normally multiply vectors, and I make sure that this is G invariant by using this Reynolds operator type thing. Okay, so the important thing is, and this is so that this is either one It is 1 if and only if it's the same irreducible character, otherwise it's 0. So these characters of irreducible representations give actually an orthonormal basis of the space of class functions. Okay, so this is also not directly obvious from here, but it's not hard to see. Another important information I can get of a character, which is also not hard to see. I mean, if I take a character and I evaluate it at the identity element, so the character of the identity element is just the identity matrix. How big is the identity matrix? Well, it's just the identity matrix, which is dimension of the vector space times dimension of the vector space. So if I take the trace of this identity, I get back, of course, the dimension of the vector space. So this is very interesting also. And
Excuse me, Corner.
yes,
So if we have the same character for two representation, so can we say anything about the representation? They are isomorphic or not?
we'll come to this in just a minute. I mean, we can use characters nicely to actually get this decomposition of representation. So if they are non-isomorphic as irreducible representations, then the inner product has to be 0. And just to mention these two things, I mean, we can completely characterize the characters in a square matrix. So it's a square matrix, namely, I mean, one entry is, I mean, the number of characters is exactly the number, because I mentioned they are an orthonormal basis for the space of class functions. So to be a basis, there should be exactly as many as we have class functions, the dimension of the space of class functions, and this is exactly the number of conjugacy classes. So we have exactly the number of conjugacy classes, many pairwisely non-isomorphic irreducible representations. That was a little bit hidden here. And the value that they take only depends on the class function. So I have class function many vectors. Each of them is class function times of conjugacy classes long. So I get this square matrix. And this square matrix is actually implemented in a lot of software systems. For example, a very famous software system is called GAP, has a lot to do with group theory, and is also available in Sage. And you can actually get, if you're interested in a specific group, let's say your favorite group, I don't know what this is, most likely its character table is available in the software. So you don't have to calculate these characters. You can just look them up in a big book. Okay, let's just see what I can use these characters for. So this is really maybe the interesting stuff. So assume I have a representation V, which is not necessarily irreducible, but which decomposes in this iso decomposition here. Okay, then the associated character is nothing else than this just means that if I think of this as matrices, that I have blocks of matrices that are, that my big matrix is made up by blocks that correspond to this direct sum here. So, the trace is very nice with direct sums of matrices. So obviously my character of this big representation will be just the sum of these irreducible characters that I have times the multiplicity, how often they appear. So I get the character of my big representation as a sum of the irreducible characters that appear. And now if I just use the orthogonality, I immediately see that if I take my character and I take the inner product with another character of an irreducible representation, I get a number back. And this number will be exactly the number of occurrences of this irreducible representation. So, you have a big book. In this book, you have a character of the irreducible representations, and you have another character that you have because of your problem. You have a representation. This is just traces of matrices. You can set up these functions. You can take the inner product, and just by calculating this, you immediately know how often this irreducible representation will appear in my previous irreducible representation. And also the the character squared, so the inner product with itself gives me exactly back the sum of squares of these numbers. Okay, so this is all just following from additivity of characters on direct sums, which I briefly mentioned, and the orthonormality of the irreducible characters. So to answer this question that you had, really having access to the characters of your representation really lets you see how this representation decomposes into irreducibles. And if you have a decomposition into irreducibles, I mean, two representations are the same or they are isomorphic if and only if they decompose into the same irreducible or isomorphic irreducible subrepresentations exactly the same amount of time. Okay, so question, I mean, now I spent a lot of time explaining this. To come back a little bit to the original question, how do we now use all of these methods to actually come up with these matrices T that I want to have concretely? And there is a very nice formula for that, which should remind you a little bit about this construction with the Reynolds operator. So it goes as this. So I have my representation V, and I define for every I is now running over all the irreducible representations. I define a new operator, a matrix. There will be a matrix. So I sum over all the group elements. I take my matrices. So these are row G's. This will be a matrix, right? I sum up all of them, and I don't only sum them up, but I multiply them with the character of the complex conjugate of the character evaluated at the element G. So just to make this remark clearer, so if my character comes from the trivial representation, one can immediately see that for every element G, this will be just one. So I essentially sum up over all group elements my operator rho G, and I divide, so the dimension then will be 1 here, W will be 1. If this is a trivial representation, I divide it just by the cardinality of the group. So this will be just then mapping V to all the permutations of V, for example, and so it will be mapping to the invariance. This will be exactly that's exactly the definition of what we defined as Reynolds operator for the trivial for defining irreducible to finding invariant polynomials yesterday. And so this is a little bit a more general concept. You can define these projections. So this will be at the end of calculating this. This will be I mean, before the V, this will be a matrix here that I have. It will be a dimension V times dimension V matrix if I really work with matrices. And if I apply this to a vector V, I get, of course, again, a vector small v in big V. And the important thing is that these projections actually map onto the irreducible representation Vi. So what I get is, so this may be a little bit unclearly formulated here. Sorry for that. So I get a projection. I mean, this is an operator that goes from V to V, but actually outside of the isotypic decomposition Vi, this will be the zero map. And inside the isotypic decomposition, isotypic component Vi, it will be the identity. This is how it is set up. Okay, so this gives me a way of actually decomposing my vector space V into the isotypic components. Okay, so this was actually, if you use this result now with what we called about what I taught about the cyclic group of order 4, this is exactly how you can actually compute this matrix T that I had in the beginning. So this worked out very finely for this example, because as you can also check in this example with the characters, all the irreducible characters, as we said, all the irreducible representations are one-dimensional. And in this particular representation, all these irreducible representations only appear once. So the theory will tell you that you expect a diagonal matrix with really just one time one blocks on the diagonal, and that you can get this with this decomposition into isotypic parts. So this is how you can actually, by using this formula, you can actually compute this matrix T that I had. Okay, let me just close with some more general remarks. So most often you actually need a little bit more work to get also the finer decomposition of these blocks yi into these blocks that I call bj, which are the blocks that that repeat on the diagonal of these blocks yi. So there is also a nice decomposition that you need, namely you need to decompose the VIs into irreducible representations themselves in a specific way. So this is a little bit more tricky because in general, this decomposition will not be unique. So the decomposition of an isotypic component into irreducible representations is not unique. So there is some choices that you need to do. But after doing these choices, one can actually also define operators in a similar, a little bit more complicated way as the previously defined, and actually get a basis of each isotypic component that further decomposes this isotypic component nicely into irreducible representations. And this is then called a symmetry adapted basis. So for people who are interested in actually knowing how to do this, this is nicely described in this book by Serre that I mentioned on Monday. So of course, we always worked over an algebraically closed field with characteristic 0, and this was important on several steps. I just mentioned now that it was actually important to use this consequence of Schur's lemma. It's absolutely possible to generalize this to all kinds of other fields. And by generalize, I mean, it works sometimes, and sometimes you need to adjust things to make something similar work. And it can be, in particular, very, very hard. So in particular, if you work over fields with positive characteristics, a lot of things can just fail if the characteristic of the group, if the characteristic of the field divides the cardinality of the group, right? Then things are very hard. And this is a whole theory in its own right, which is very beautiful and very, very demanding. And I did all the things I mentioned here so far, and in particular this example, I focused only on finite groups. And since somebody asked yesterday, yes, this can be also generalized to a much wider class of infinite groups. And if you're interested in that, because you have an example where you have, for example, the orthogonal group acting on something, and there is the keyword that you want to look for is the so-called Peter-Weil theorem, which is sort of a generalization, or it's generalizations of Schur's lemma and the consequences to this infinite case. And the message again that I want you to take home is that I hope I could hand you a toolbox of representation theory that is a handy thing to keep with you for the rest of your mathematical career, because instances of this will appear many times in completely unrelated fields, first-hand side unrelated fields. And we will see two examples tomorrow, or one example tomorrow, maybe one on Friday, where this is actually something that can help you a lot to understand a situation where a group is acting just by understanding a linear space and how this decomposes into irreducible representations. And with this, I'm almost done, and I want to close with another nice picture of what you can see if you are in Tromsø, namely, again, the northern lights that I could see from where I actually live. So this was taken at the place that I live. And again, I want to briefly mention that if you are a PhD student or you want to be a PhD student, if you are a PhD student, then it's maybe too late. But if you want to be a PhD student, here's a possibility. And if you know talented people, please feel free to direct them to this call. Thank you very much.
Thank you. Thank you very much. So are there any questions from the audience, from Karachi or from the online audience?
Sorry, I just wanted to ask about this tensors PhD position. So I was reading about it after you showed it to us, and it says that if you live in the same country where the PhD position is being offered, then you can't
Yes.
apply for that specific PhD position?
Exactly.
Is
Exactly.
that strict? Or
Unfortunately, yes. Okay, this is something that unfortunately I should have pointed out, but I was not careful here. This is money that is funded by the European Union, so they have a rule that you are not allowed to have lived in the country where you will be going for more than 2 years in the previous 3 years. So let's say if I, because I'm originally from Germany, want to go back to Germany, I could because I have not been living in Germany before. But for example, I have been living in Norway for quite some time, so I could not apply for the position in Norway. This is unfortunate. Yes, I should have mentioned this maybe previously. But if you look around, I mean, there is actually many other positions in, I mean, there's not just one country in this network.
Any questions from the audience in the IBA Karachi? Or comment?
So,
Yeah.
can I? Yeah, so I'm just, are you going to somehow talk about the action of these cyclic groups on like, let's say CN and talk about what happens there, similarities and how you can get the resolution from the using the representation theory?
So you mean CN, cyclic group of order n, or?
No,
Yeah, I
complex
mean,
number.
action of the cyclic group on any complex n-dimensional space, for example.
So this is a very good question, and I mean, this would be exactly the answer to the question that I asked in the beginning, like why? And I claim, okay, this is now maybe this is a bold claim, and of course now you feel, I mean, people might feel intimidated if I say it like this, but if you followed, I mean, I gave you a recipe, hopefully understandable, for the case n equals 4, and the same recipe will follow also for the other n's. And if you have specific questions, I mean, if you try to do this and get stuck or so, feel free to reach out. But the idea is, again, for an n-dimensional representation, define a nice n times n matrix where then the nth root of unity appear in this magical way, which exactly corresponds to the characters that you can find online also. So these are exactly these assignments to the different roots of unities. And you look at your matrix, you multiply it from the left with the inverse, you multiply it with the right, you will get the diagonal matrix, and you will actually be able to see what happens on the diagonal. So this is actually the way you would prove the theorem that the determinant is always the product of these linear forms.
Okay, Professor Rina, in this particular case of circular matrices, I guess all you have to do is take the Fourier matrix, and that'll be
Exactly,
the eigenvectors.
Exactly.
And, yeah.
Exactly. I mean, this is another, and the matrix that I used, I mean, you have hopefully or maybe seen in other concepts this whole business of using abelian groups, and the representation theory of abelian groups magically also appears in what we call Fourier analysis, which is actually very highly related to representation theory. So Fourier analysis normally works with abelian groups, finite abelian groups, but you can also do Fourier analysis for non-abelian groups, and then it's essentially, I mean, it's the same thing. I mean, it's the same ice cream, just with another taste, if you want to say it like this. So it's, if you understand one, you will understand the other. It's maybe a question of taste how you present it, but exactly the right keyword that I should have mentioned is the Fourier basis. Is exactly what this matrix contains, is normally called Fourier basis. Thanks for that.
Okay, I hope everything concluded with this session. Thank you, Cordian. Thank you very much. Cordian, one request, would you be available on today's research discussion session at 4
When
p.m.?
is it? Yeah, it should be.
There is a discussion, research problem, open problem discussion session scheduled today at 4 p.m. So would you like to share?
Yeah, it should be fine. It's 12. I mean, I'm just, this is the only problem is that I always have to keep in mind that for which direction the time goes, but I think 12 my time should be fine.
Okay.
So I just log on then.
Okay, so so the main thing you are not going to show up at 4 p.m. Maybe now you will show up in tomorrow. That is what I understood.
No, I will show up at 12 o'clock my time, 4 o'clock your
Oh,
time,
okay, okay,
and I
okay,
will just follow. No, this was the question, if I follow.
okay.
Or
Thank
should I
you.
also present something?
Okay, got it. Thank you. Thank
Pardon
you,
me, I
everyone.
was just saying sorry, it's a little bit complicated when you're of course not there. So, but I would really like to hear this.
Okay, thank you. Okay, it's time for lunch, and thank you, Cordian. Thank you very much once again. Thanks,
you
the
later.
speaker. And thank you, everyone. Now it's time for lunch, and we will reassemble here at 2:30 sharp. Thank you.